So we have already completed the module 2. Okay, that is the oscillation. Now we start module 3. Optics. Module 3, optics. Silent. In our bridge course, we have already discussed the interference, and in your syllabus there is no interference. You will start from the diffraction. Okay. So first is diffraction. What is interference? What is interference? Superposition of two waves coming from the same direction. Okay, and in the screen we get the dark and bright fringes. Okay. Now what is diffraction? Good. Okay. So diffraction is the bending of the light from the sharp corner and distributed in the geometrical shadow region. That is called the diffraction of light. Okay. Now, still now you know that light travels in straight lines. Okay. So now, how the light bends? It cannot bend from any corner or any sharp corner. So what is the sharpness? Because from here light cannot bend. So they can only diffraction with them. You can get the diffraction here also. So the sharpness is comparable to the wavelength of light. Okay, that is sharp that is the wavelength of light, that is the angstrom order. Then we can get the diffraction. So how will we find the diffraction, or we can see the diffraction? If you take a new plate and if you put in the sunlight, then you can see that there is some colors in the plate edge. Okay, that is the diffraction. Okay, that is the light came and bent on that sharp corner. Okay, that is the diffraction. So what happened? If there is a source here, then this is the slit. Then this is the light portion. This is called this portion, and this portion is called geometrical shadow region. So this is the source of light, and we get the diffraction pattern here and here. Okay, diffraction pattern in the geometrical shadow region. And if there is an obstacle here, then if this is the screen, then this is the light portion, and we get this is the geometrical shadow region, and we get the diffraction pattern here now. Okay, in geometrical shadow region. Now, write down the definition. হয়েছে। Now write the definition. The phenomenon of bending of light waves. The phenomenon of bending of light waves round the sharp corner. Bending of light. The phenomenon of bending of light waves round the sharp corners. Round the sharp corners of obstacles. Of obstacles, OBSTACLES, or slits. Obstacle or slit of sizes comparable to the wavelength of light. Of sizes comparable to the wavelength of light and spreading into the geometrical shadow region and spreading spreading into the geometrical shadow region. Geometrical shadow region is called diffraction of light. Is called diffraction of light. Okay. The diffraction of light is divided. Next paragraph. The diffraction of light is divided into two classes. Number one, two classes. Number one, Fresnel diffraction. And number two, Fraunhofer diffraction. Fresnel diffraction and Fraunhofer diffraction. Now you have to write down the difference between interference and diffraction. The difference between interference diffraction of 3 seconds, CO goes outcome is 3, CO3. Difference between interference and diffraction. So when you write down any difference, you must write in 2 colors. Interference, diffraction. Okay? Number 1. In interference, number 1, in interference, the superposition of light waves, is due to two separate wave fronts. Originating from two coherent sources. Okay, so superposition of two wave fronts, and the two waves coming from the two coherent sources. What is coherent source? Monochromatic light and have the same phase or a constant phase difference. That is called the coherent source. Okay, and we get two coherent sources only from one source. Okay, two different sources never be a coherent source. Okay. In diffraction, number 1. In diffraction, the superposition of light waves, is due to secondary wavelets, 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 wave fronts, wavelets, originating from different parts of the same wave front. That means if this is the source of light, then we get the wave fronts like this. This is the wave front. Okay, and from this one wave front, same wave front, these are the wavelets. So when we get the superposition of these two wavelets, then we get the diffraction. Okay, from the same wave fronts. Number 2, interference. The regions of minimum intensity, are perfectly dark. Diffraction, number 2. The regions of minimum intensity perfectly dark. Are not perfectly dark. Okay, so why in case of interference it is perfectly dark? What's happening in case of interference? When two wave fronts or two waves coming from the same source, but two slits are there. Coherent source. So what is coherent source? Monochromatic light, and they are in the same phase. So when they are in the same phase and when they meet here, then what's happened? When this and this meets, then we get this one, and when this and this meet, we get the dark. Okay, that is the amplitude is same, and one is 1A plus A, that is 2A, and there is A minus A, that is 0. So why? It is perfectly dark. Intensity is the square of the amplitude. Okay, intensity is square of the amplitude. So when there is a dark fringe, that dark fringe is perfectly dark because it is a monochromatic coherent source of light. That is, the amplitude is same also. That is, A minus A equals to 0. Amplitude will be 0. Resultant amplitude will be 0, and we get the interference like this after superposition. Okay. And in case of diffraction, why it is not perfectly dark, we will discuss it later. What's happening in case of diffraction? In case of diffraction pattern, if this is the diffraction, then inside the diffraction there is also some interference pattern. It may be happening when there is a dark for the diffraction, there is the maximum for the interference. So when these two is superposed, then we get some light. Okay, so why? In case of diffraction, here we don't get the perfectly dark fringe. But I'm not going to discuss this. Let me discuss the theory. Number 3. The width of interference fringes, the width of the interference fringes, the width, W-I-D-T-H, thickness, the width of interference fringes may or may not be same. Fringes may or may not be same. Okay. In diffraction, number 3, the width of diffraction fringes, the width of diffraction fringes are never equal. Are never equal. Okay. On the interference fringe, beta equals to d lambda by d. All are constant. D is the distance between the screen and the slit. Small d is the slit width. Lambda is the wavelength. So all are constant. That means beta is constant. But in case of diffraction, again we will derive that beta is not constant. As we go from the central fringe to the outer side, the fringe width decreases and ultimately vanishes. We have already done the experiment with the multilateral light, and you must see that the central fringe is bright and large. As we go for the first, second, third, fourth order, it will decrease and ultimately you don't get any fringe. Okay. Number 4, intensity interference. All bright fringes all bright fringes have the same intensity. Same intensity. In the diffraction number 4, the intensity of the light, the intensity of the bright fringe, usually decreases with increase of order number. Okay, so as I told you, in case of laser also you can see that the intensity of the fringes, bright fringes decreases and ultimately it vanishes. We don't get the intensity after some order. Okay, so these four are the difference between interference and diffraction. Now the second one, difference between Fresnel and Fraunhofer. Fresnel and Fraunhofer diffraction. Difference between Fresnel and Fraunhofer diffraction. Fresnel diffraction. Fraunhofer. Fresnel and Fraunhofer diffraction. Number 1, Fresnel. The distance of the source or the screen, or both from the diffracting elements are finite. Okay, diffracting elements are finite. So what is the diffracting elements? Slit or obstacle. Okay, so from the slit or obstacle, the distance of the source, that is light source, and the screen is finite. Okay, within finite distance. So in case of Fraunhofer, number 1, the distance of the source or screen or both from the diffracting element is infinite. Is infinite. Okay. So how we get the distance infinite in our laboratory? Laboratory infinite distance like that. So how we get it? What is the wave front? What is the wave front for the infinite light source? Parallel. So how do you get the parallel light in laboratory? If we put a convex lens, a convex lens is a response here. So we have the parallel light here. Okay, that is the infinite distance. Okay, our body is going to left is convex lens, and parallel light at point here. Speed of infinite. Okay, in this way we get the infinite distance. Now, number 2. In Fresnel, the wave fronts are not plane. The wave fronts are not plane, but spherical or cylindrical. But spherical or cylindrical. Spherical or cylindrical. Number 2, front of what? The wave fronts are plane because it is coming from the infinite distance. The wave fronts are plane. Number 3, Fresnel. The diffraction pattern is not well defined. The diffraction pattern is not well defined. That means the diffraction pattern is hazy. Bright fringe opore dark fringe chole aste pare. Okay, it is not well defined. 3, front of a diffraction. The diffraction pattern is well defined. The diffraction pattern is well defined. Number 4, Fresnel. The incident rays are not parallel. The incident rays are not parallel. Finite distance they are not parallel. And 4, form of what? The incident rays are not parallel. And 4, form of what? The incident rays are parallel. So these are the 4 differences, okay, of Fresnel and form of what? And interference and diffraction. Today, this one, because after that we have to derive the expression for the intensity for single phase diffraction pattern. It will take time. So we'll discuss it in the next class.